You know, I'm an organic chemist. I grew up, I learned about chemistry, organic chemistry, by playing with these types of three-dimensional models. When I wanted to start making protein-sized objects with these models to really look at them in 3 dimensions, of course, there's limitations. These don't have, you know, Drying models actually have nice motion to them. CPK models are heavy and kind of static, and you know, these all have deficiencies. So what we set out to do was create a dynamic 3-dimensional model of the protein. And I became, you know, interested as I was explaining to students how this worked. You know, we think about a protein as a repeat of amino acids. Of course, that's what we're taught. And that the point of connectivity are these, you know, red linkages. The problem with this view is that it doesn't reflect the actual motion of the atoms. And so from, you know, as we also learn in textbook, the amide units are planar, and the only bonds that really rotate are these phi and psi dihedral angles. So if we're going to build a model, rather than make amino acids that link together, what we really want to do is create amide units that are connected to alpha carbon units. So now these red connectivity points are the phi and psi rotation angles. And this is now essentially, you can think of this as an alternating copolymer, where the alternating units are amide units and carbon units. And those are repeated in an alternating fashion. And so then when we look at, say, a helix in computer representation, we can convert that to amide units, which these amide units are all planar and rigid, connected by these alpha carbon units. So here's an alpha carbon with 2 amides. And this is what it would look like. And then here's a model representation of that unit. So then it's a matter of building each of these pieces and connecting them with rotatable units. And so here are the parts that we developed. And so these are plastic parts that can be printed on a 3D printer. This is an amide unit, so this is 4 atoms, carbonyl, carbon, oxygen, and a nitrogen and a hydrogen. This is an alpha carbon, and it has its own hydrogen. And then there's a side chain unit. At this point, we just have a methyl group. And then these are just screws with a little nylon bushing that can spin freely. And so we have a little bearing. So the idea is to create a model that can be as flexible as an actual protein. And so here's an assembled unit. You can see the alternating amide alpha carbon units. We've color-coded the oxygens as red and hydrogens as white. And here are the methyl groups, so that's an alanine side chain. And then we wanted to introduce some of the natural forces that are also present. So we introduced magnets here. There's magnets embedded in each of these oxygens and hydrogens, and those represent hydrogen bonding. So this allows you to connect disparate parts of the molecule to create hydrogen bonds. And we tuned the strength of these magnets to compensate for the actual physical weight of the object to hold them together. And so here's an alpha helix, and holds together very nicely. And you can come up and play with these. So in order to produce these, we use a 3D printer. And we're making 16 amide units here. This is about an 11-hour print, condensed to about 30 seconds. And so these are printed, and then we remove the support material. And then for the amide units, we have to actually, 3D printing is not perfectly precise, so we bore out these holes. They're printed a little undersized, and then we can get a perfect diameter and then put in the bushing to create the rotations for the bonds. And these all these parts are available on the 3D Print Exchange, and there's a tutorial in the Make magazine on how to put these together. So what we wanted to do is, capture the idea and learn about the dynamics of the structural changes. And this is why I really went to all this trouble, is to really understand. I learned about Ramachandran plots in whenever that was, a long time ago. But really being able to visualize why, when you have this point in the Ramachandran plot, you have an alpha helix. And then when you move to this point, you get a beta sheet. And so understanding exactly what those dihedral angles look like, and you can play with it on the model. Here you can see these are the changes that happen in psi going from a helix to a sheet. There's about 180-degree rotation. And in phi, when you go from a helix to a sheet, there's a smaller, more modest rotation. And so, it's those two rotations that give rise to this major structural change. So what we wanted to do was actually reflect some of those propensities. So actually this Ramachandran plot is actually a histogram of all the protein structures in the protein data bank, showing the frequency. So you can see that there's a lot of alpha helices, a lot of beta sheets. We wanted the physical model to reproduce that preference for the model to prefer these bond angles. And so what we did was introduce magnets into, you can see them here, they get kind of hidden from view when the model's assembled, but these magnets attract each other such that when the bonds rotate, they prefer to stick at certain positions. So we can actually, so here's a bigger version of this, showing a certain pattern of magnets, and so when I spin this around, it always wants to stop at certain preferred locations, but I can still rotate it around. So it's the idea that there's an energy minima at certain bond angles. And so we reproduce that in the magnets. And so here you can see the amide unit is this piece, alpha carbon unit is this piece. When we mate them together, here's this free spinning bearing, but these magnets are held pretty close to each other and prefer certain angles. So we actually went to the trouble of quantitating this to make sure that it was roughly approaching what we see in the protein data bank. And what we're looking at here are blue is the distribution of bond angles that we see in the protein data bank, and the red are showing the rotational barriers that we measure by putting these magnets in. And so you can see that for psi, we actually have very accurate reproduction of what we see in the PDB. And for phi, it's not quite as good, but still centering this region of angle space for the model. And so the way that we measure this is using a little torqueometer. Basically, this is the same little unit here, and we just rotate this and measure measuring the current. So we have a motor here driving this, and we measure how hard it is to push past these barriers. And so this just showing this motor and the amount of current drawn by it is shown here. We can plot that, and that's roughly a measure of the torque. And so we can design different rotational barriers into the models this way. And you can see here's the Ramachandran I showed you before from the protein data bank. Here's the model. Here's what we get from our crude magnet device, and you can see not a perfect match, but pretty close match. Of the blue is the more preferred bond angles, and so our model prefers to rest at the same place as real proteins do. And these red areas are sort of the physical occlusions where the actual plastic bumps into each other, which is true in the atoms as well. So now we have a pretty accurate representation of the backbone and its dynamics. And so we can fold this into alpha helix. We can fold it into parallel or anti-parallel beta sheets. Here I have a beta sheet. And it's actually really interesting to actually feel this and feel there's some rigidity to it. You can feel that there's some torsional resistance due to all of those magnets working together. And I think it's really a great example of how multiple weak interactions work together to stabilize a structure. And I think that's one of the fundamental challenges in design is to anticipate how all these weak forces are working together to build something strong. And you can see here, if we look in more closely, you can see that in the beta sheet, these magnets are aligned, and in the alpha helix, they're also aligned, but in an alternate configuration. Finally, we've been doing some outreach here. I've gained a lot of insight from it, but we realized that this is a great way to engage the public and students, from kids, but adults also really have enjoyed this a lot. And we're just looking for other ways to explore getting these models out there. And finally, I want to thank my really talented student, Promita, who did this as part of her thesis work with Alexei Anufriev at Virginia Tech, Julian Muzard, who's a visiting scientist with me, and Allison Chen, who's a high school student. And thank these funding agencies, and thank you for your attention.
And the line to play with those at the break will be behind me. Thanks a lot.
Sure.
I'd like to introduce Amy Robinson. She's the executive director of iWire, a game to map